Okay, welcome back to lecture 23.4, where we're going to talk more about first order phase transitions. All right, so last time we talked about how when we have little g, which was big G over m, as a function of temperature, and we had two phases. Let's see if I can do a good job of drawing that. Yeah, better. We would have one curve and another curve, and there's an actual discontinuity that happens at TC. And that led to a change in, now this is the specific entropy. So this would follow something like a jump in the entropy. And then this had some latent heat associated with it. And so we called this a first order phase transition. But remember, when we had our partial derivatives for G, we not only did we have that S was minus partial G partial T at constant P, but also, let's just write it over here. S was minus partial G partial T at constant P, but also we had the volume was partial G partial P at constant T. And so if we look as in a similar way at little g versus pressure, and then the volume versus pressure, what do we expect to find? Well, again, we expect to find a discontinuity. So you can find this actually graphed pretty nicely in on page 175 of Finn. This is chapter 9.5, 9.6, 9.7. So what should it look like? It should look like this as a function of pressure, where this is the liquid and this is the solid. That is, when you go from the solid to the liquid, the volume should jump up. Let's see if I can line those up a little bit better. So at TC, the volume should jump and have a discontinuity. Okay, think about this. As we increase the pressure, the volume goes down, and at some point you get the volume to go down so much that you turn from a liquid into a solid, right? That is always true. All known materials, that when you compress them, the volume goes down. Okay. So that's our second discontinuity, both in our entropy per unit mass and our volume per unit mass. I guess that would be our density. But we still haven't answered exactly how we can have two phases coexisting, right? At these phase transitions, how can we exactly have two phase transitions? We know that, so at a phase transition, right, we have this unusual behavior of two phases coexisting. And so how does that happen? Excuse me. Okay, so we know that at equilibrium, so if let's say we sit at this temperature, right? So imagine sitting at the phase transition, whatever phase transition it is. We are in equilibrium, right? And so infinitesimal variations around that would be zero. We're in equilibrium. So we have no spontaneous processes driving the system. How can we have two phases that exist in exactly the same place? I think that's really unusual, right? That is, G is a minimum. So how do we understand mathematically what's happened there? Okay, so because the free energy is, so imagine two phases. We're going to call them phase one and phase two. And we're going to ask the total free energy of this system. And that can be extrinsic, energy is extrinsic. So we can actually just add up the energies of the two separately, right? But there's a mass associated with each one, a quantity associated with each one. And so we can say that, for example, G1 is the mass of 1 times little g, 1. And G2 is like the mass of G2 and G2. But we also know that the total mass must be conserved, right? So this must be conserved. Okay, so let's imagine what happens. So if we write G as M1 G1 plus M2 G2, but if we're sitting at TC at equilibrium, dg equals 0. So we can say that dg equals dm1 G1 plus dm2 G2 equals 0. But mass was constant, right? So we know that dm is dm1 plus dm2 is equal to 0. That is, dm1 is equal to minus dm2. So let's put that in there. We can say that, for example, dm1, let's write g1 dm1 equals minus g2 dm2. So we can write g1 dm1 equals, well, that's minus a minus, that's g2 dm1. And those cancel. And we can say G1 equals G2. So this is actually what happens at a phase transition. Okay? The masses, right, of the relative phases. So, for example, I can convert, say, solid to a liquid, or liquid to a solid, or solid to a vapor, or liquid to a vapor. But the individual intrinsic free energies per unit mass are equal, right? So that's what we've been plotting here, is that the little g's, those are equal, and I just convert mass from one phase to another. And that's perfectly okay. So I really like that idea that the equilibrium is defined by this minimization of the free energy. And at Tc, we're just converting mass from one to the other. But as we do that, we're pulling out that latent heat, right? Or adding that latent heat. And so that's really what's going to be satisfying that third law of thermodynamics. So I think that's really beautiful stuff right there. And really motivates a lot of what I think as condensed matter physics, this looking for these phase transitions. Okay, next time we're going to do the Clausius-Clapeyron, so stay tuned.